Okay, good morning, everyone. It's 8 o'clock in Prague and 9 o'clock in Palanga. So I suppose the session is about to begin. I'm your chairman today. My name is Jaromir Hrad. I'm come from the Czech Technical University in Prague, and I've been asked to chair this session that deals basically with automotive electronics and its applications. So today we have scheduled 5 papers for the morning session. As far as I can see, at least 4 presenters are here. And in the meantime, Darius is checking about the 4th one. So I guess we can begin. Just briefly recapping the rules. Every presenter has allocated the total of 15 minutes for the presentation and 3 minutes for possible discussion so that we are able to conclude the session in about 90 minutes. So the first paper we have today is from Romania, from Craiova, from the Department of Robotics at Hrad, yes. And presented by Horia Vladut Caprita, and his co-author is then Selisteanu. It's about automotive sensors and some, let's say, switching between software and hardware, I suppose, in order to relieve some functions. So please go ahead, the floor is yours.
Okay, thank you very much. Good morning, everybody. I will share my screen. Okay. Just a moment. Do you see my presentation?
Yes. It seems perfect. Thank you.
Yes. Okay. Thank you very much. So my name is Horia Caprita, and together with Professor Dan Selisteanu, we propose to present today this paper, Improvement of Automotive Sensors by Migrating AUTOSAR End-to-End Communication Protection Library into Hardware. Shortly, I will go to the introduction. Basically, in this paper, we propose a new method for increasing the safety level of the data transfer between the sensors and the electronic control units inside of the car. This new model of the basic sensors contains the hardware modules that implement the end-to-end communication protection mechanism as it is defined inside of AUTOSAR architecture, software architecture, which is a standard in nowadays automotive developments. We want to add this feature inside the sensors in order to develop sensors that can be directly connected to the automotive network, like lean, CAN, FlexRay, and etc. Finally, we implemented this model inside of an FPGA in order to validate the results and to be able to check our outputs to be used by the ECUs inside of the car. So basically, the safety inside automotives are it's established based on 3 factors: severity, exposure, and controllability. Severity means damages in case of system failure, exposure, probability of failure occurrence, and controllability, the control degree of the system in case of such events that can occur. And based on this, we have several levels of safety defined in this standard ISO 26262. There are 4 levels, A, B, C, D, where in case of level A, we have minimum level of risk, and D, maximum level of risk. These levels are applied also on hardware, software, and system in automotive. And these levels are required by our clients, of course, depending on the functionality having in view. The car architecture right now, we have inside of a car tens of hundreds of electronic control units, which are dedicated for controlling the functionalities, for different functionalities inside of the car. All these ECUs are connected via communication networks, And it is very, very important that the data that are transferred between the ECUs to be protected in order to assure the safety level for the presented car. From the software perspective, all the applications must fulfill the requirements of the AUTOSAR software architecture, which looks like this in this case. Inside of this AUTOSAR, there is a mechanism proposed end-to-end communication protection, which is working like in the computer networks. For example, one ECU, ECU1, is the sender. Inside of the software, this ECU must protect the data before the data to be transmitted over the communication infrastructure to the ECU2, which is the receiver. On the receiver side, this software will check the data received on the communication bus, and if everything is okay, the data will be used inside of the software. So this is basically the end-to-end protection software mechanism. This end-to-end protection software mechanism is integrated in software in this communication stack inside of the software, which is running on microcontroller. How this end-to-end protection is working? Basically, we have many signals which represents the digital value of the physical value which were read from the sensor or which should be sent to an actuator. End-to-end protection mechanism will calculate a CRC, a cyclic redundancy code, over all of this signal inside of a message on the bus, and in addition on a counter, which is usually rolling from 0 to 15. Our proposal is the following. Right now, the basic sensors are connected inside of the car directly to one ECU via standard interface, let's say serial peripheral interface. The ECU1 will have the role to interpret the data read from the sensor, to protect this data by adding the CRC, and this CRC, it's a software CRC, is not related to the CRC that is implemented inside of the protocol inside the driver, the hardware driver. And the ECU1 will provide this data via the communication bus, link, X-ray, Ethernet, and etc. towards other ECUs. Our proposal is to change these basic sensors in order to be able automatically to protect the data by using a hardware module and to put this data directly on the communication bus. So basically all the ECUs will have access to this data directly without an intermediate ECU or dedicated ECU. We proposed in this paper a message which looks like this. We have only one signal. It's signal A on 8 bits. We have the counter, which is rolling from 0 to 14. The value 15 means an error. And we have the CRC, which will be provided by the sensor on the bus after the value is calculated by the hardware. The logic diagram of the CRC calculation is presented here. It's a standard CRC calculation, and it is based on a lookup table of 256 elements. It's a standard lookup table and standard values. And basically, in this loop, there are some exclusive OR operations between the initial CRC value and a value inside of the lookup table, and so on. How it looks, our hardware. It is based on a clock generator, of course. We have an input buffer of a data ID because this end-to-end protection specifies this data ID value, which is an identifier for the software which will consume this data. It is very important. We have a counter signal. And we have, of course, the value of the signal A, which is produced by the sensor. We have a fourth state machine, which is used in order to handle all the logic diagram that I presented in the slide before. We have CRC8 computing logic. We discussed about a CRC8 bits value. And the output buffers, which are used to store the message, the values of each byte inside of the message for the CRC counter and signal A. And of course, these values will be put on the bus or will be sent on the bus driver, which can be LIN, CAN, FlexRay, or other protocol. And this bus driver will have the role to put the data over the communication network. How it looks inside of our simulation of the hardware inside of FPGA. Basically, the CRC, which can be seen here, in this case, value 55 in hexadecimal. This value will be produced during 4 cycles inside of the hardware. The output data rate for this hardware is 1 millisecond, which is a period of time acceptable for CAN, FlexRay, and other protocols. And we can see that these 4 states are produced using 16 clocks. The period of the clock is 62.5 microseconds. How it looks, the block design of this hardware, I put here a detailed design only for CRC8 computing logic block. And we'll see here in the center that we have the XOR logic for making the operation exclusive OR between the lookup table and the data produced by the sensor. And if you are looking inside of such module, RTL means runtime library. All these RTA modules were developed by us using Verilog language. If you are looking inside of this module, for example, it's a data selector, and as we expected, the elaborated design for this block design is based on multiplexer. When we implemented the design in FPGA, we observed that our hardware module for the message proposed by us occupies inside of FPGAs occupied 13 CLBs, means 13 configurable logic blocks. This is the board that we are using in our development. Experimental results, basically the utilization rate of the FPGA takes 46 lookup table elements, 30 flip-flop registers, 1 block RAM, and 54 input-output pins. Of course, if you want to implement a message bigger than 2 bytes of useful data, this utilization rate will increase. We simulated our implementation inside of Vivado tool provided by Xilinx. As I said, clock signals is 62.5 microseconds, which means the data output rate will be 1 milliseconds. Counter signals is rolling between 0 and E, 14 in decimal. You can see that counter values here inside of this table. And we kept signal A on a constant value A5 in order to be able to validate our data. And we proposed data ID to be a constant value to 1. This data ID is specified by the client. The results can be seen here. We see here the evolution of the counter, which is quite good. And also we have here the evolution of the CRC, cyclic redundancy code. Now, this model should be validated. So in order to do this, we used hardware and software provided by Vector. Vector is the most important provider for such tools for automotive. And of course, we use the real CAN bus and ECU used in automotive from here, from Continental. And we compared the values provided by our FPGA implementation with the values provided by the real system. And we'll see that the values are identical, which somehow validates our model. In conclusion, this end-to-end protection communication mechanism is feasible to be implemented in hardware. As we see, the integration in FPGA for a message of 3 bytes length, and I mean here 1 CRC, 1 byte for CRC and 2 bytes for data, took 46 lookup table, 30 flip-flop register, 1 block RAM, and 54 input-output pins. The utilization rate for internal modules is 0.1%, while for the CRC lookup table is 0.83%, and for input-output pins is 13.5%. Of course, if you increase the number of bytes, as I said, it's clear that the utilization rate of the internal modules will be affected. And as I said, the proposed hardware is able to provide data on each millisecond, which is quite fast for automotive network. For example, for CAN, it's a good data rate. FlexRay, for example, is able to send data on every 5 milliseconds. So we cover also the FlexRay protocol here. Future work will consist in designing the end-to-end module to process many signals for a message, of course, bigger message for many bytes. Also, we want to improve our concept in order to implement all the profiles or several profiles for end-to-end communication library, because there are many profiles defined in the AUTOSAR and we have to cover all these profiles. Also, we want to integrate inside of the hardware the receiver part of the end-to-end communication protection. Basically, we want to implement a checker in order to implement, let's say, the end-to-end communication protection inside of actuators. And in this case, we can connect an actuator directly on the communication bus. So, of course, if the results will fulfill our expectation, then basically this sensor or actuators can be used directly in the future automotive industry. Thank you very much for inviting us to be part of this conference. Thank you very much for the organizers, and thank you very much for the reviewers, because it was a very valuable experience after we received all the observations and that's it. Thank you very much.
Thank you. Now, let me open the floor for possible questions. So please, are there some questions, some requests for comments? I cannot see any hand raised, or I don't hear no feedback directly. My concern is because I can see that you work for Continental, so I suppose that all of these details you have just described are intended for practical application in real production. And the question is, how about the speed? Is it sufficient? I mean, you know, I'm not an expert in automotive electronics, so my concern is about the speed of, let's say, sampling the states of the sensors. Is it satisfactory with respect to safety and that kind of things?
Yes, it is. And basically, this idea comes from the reality. We are doing this daily in our projects, and all the time we are facing with such situation like, for example, the ECU, which is responsible to provide the data over the communication bus, is failing because of the hardware issues or because of the software implementations. There are bugs that maybe in some special cases are not discovered either by Continental, either by our clients, BMW or other companies. And these issues are revealed only in field when the car is already sold to the clients and so on. So by having these sensors that are able to be directly connected to the communication bus, these sensors are, of course, very strong, tested by the producer and so on. And we can avoid such failures. We can avoid a lot of hours of work in order to checking that issue that maybe has some issues and so on. On the other hand, right now we are in a very big crisis on semiconductors. You know this. Right now we are facing with the following situation. We have to change a lot of sensors because they are no more available. Our partners provides us different type of sensors with different characteristics. This means we have to update all the software and in some cases the hardware for the ECU, which is responsible to work with this sensor. If we'll have a standardized interface on CAN, FlexRay, and so on, then of course we can change the sensor. The sensor will provide the data over the CAN, and in the worst case scenario, we have to update only some values inside of the new software in order to interpret in the right way the digital value on the CAN bus, for example. We don't have to adapt the hardware, the interface, and so on. And this will be a good point for us.
I see. I guess that would be a very interesting discussion, but unfortunately we're limited in time. So
okay.
Thank you once again. I'd like to ask once more if there are any questions or feedback from the audience. Well, if not, I'd like to thank you once again. And I will invite the second speaker of the present session, who shall be Giovanni Battista Gaggero from University of Genoa, Italy. And the keywords for the second presentation shall be agriculture vehicles, security, and automation. So please.
Thank you very much.
Stop sharing, switch your screen off, and let's invite Giovanni to present us with his paper.
Thank you. Good morning, everyone. Allora. Share. Okay, can you see my screen? Can you hear me?
Yes, it's all fine. So please go ahead. Thank you.
Thank you. Okay, good morning, everyone. I'm Giovanni Gaggero from University of Genoa. The problem? Our problem was to assess the security of devices like that. This is an automated agricultural machine that is able to work both on autonomous mode, so you can upload maps and the vehicle estimates its own position. It can do whatever it has to do in the field, or you can teleoperate this machine. So you have a sort of joystick and you control remotely, viewing the machine what is doing. And in order to develop a sort of framework, so to develop guidelines and procedures to assess the network security of these devices, we try to generalize the network architecture, and we find actually that the same control network is shared also by other type of automated machine in the agricultural domain, but also a little bit farther than that. For example, some tower cranes has pretty much the same control network that is composed like this. You have a CAN bus, and directly connected to the CAN bus, you have different control related device, let's say. First one, as I said, this is a vehicle that can work autonomously, so it has a GPS and some sensors to estimate its own position. Then it's not very frequent, but you can also find gateways to remotely control the machine. So, for example, you can find gateways like CAN bus to Wi-Fi that allows you to send Wi-Fi packets that are converted into CAN, and the packet directly flows into the control network. It's not a much secure solution, but you find many examples of that, especially in the case of agricultural machine. And last but not least, you can control by remotely control the machine by using different protocols, both well-known protocols like IoT, for example, low power wide area and so on, but also you can rely on proprietary solution protocols of which we don't know nothing, and we would match especially on this part. So to assess the security, the network security, let's say, of the machine, we focus on 4 different pillars that are the security of the control network, of course. It is based on CAN bus. Then the security of the gateway, the security of the position estimation, so how the vehicle can estimate its own position, and the security of the remote control. In this case, was based on a radio link. So we developed a testbed acquiring basically the control network of the tractor that I shown before. And we can see that we have an ECU with 2 buses that actually was connected. So in most time, you have only one bus, one CAN bus for all the control device of the machine. On the bottom, you can see the transmitter, so the joystick that allow you to remotely control the tractor, and the receiver that again is directly connected to the CAN bus. And to interact with this control network, we used some vampire tap to just connect, electrically connect to the cable of the CAN bus and try to inject packet, but mainly to verify the success of the attacks we are performing on the radio link. So the idea is we try to perform some attack with our SDR car, and we see, starting from the fact that we don't have the whole tractor, we see if the attack had success, checking if the corresponding CAN bus packet is flowing within the CAN bus network. Starting from the CAN bus, actually there is not much interesting to say about the protocol. It's not a secure protocol. For how it is designed, the frame, for example, you can see that there is no address of each device. You have only an arbitration field, so just sending packet with the highest priority, a list of zeros you can implement with 10 line of code a denial of service over the canvas. And the problem is that there are actually some solution for improving the security of canvas control networks, but they are not very common, especially in the field we are working on, that is agricultural and automated machines. For example, there are in literature some proposal for encryption of the whole packet of the canvas, but you find many problems about implementing that in real vehicle, and of course for computational complexity that needs each node of the canvas, you don't find nowhere, let's say, in the agricultural domain. There is also a little bit more light authentication method, but again, we verified that in our test, but there was no authentication methods. A little bit much interesting could be a sort of network segmentation. Let's say if we imagine that these machines could work outside, so can be reachable by everyone. The point is that if, for example, you have a sensor outside the car, if someone can access this sensor, he directly connected to the wall control network, so it can reach the engine and so on, or you have a sort of network segmentation of the canvas. This is open question when you verify the security of this machine, and in our case you have only one bus, so if you can reach a network, you can inject packet, and the action is performed by the tractor. So we didn't have we discovered nothing new on the canvas. It's well-known information. More interestingly, as I said, this is an automated machine. Sorry, I'm mixing some results that are presented in the paper as something new, but we are working on that at the moment. As I said, the machine can work autonomously, and the question is how it estimates its own position. Because if it relies only on GPS, then it's quite simple to perform some attack on the GPS, like GPS spoofing. This is an attack on which you can basically overlap the signal of the satellite, making the vehicle believe that is in another position from the actual one. You can find tools and also open source software online for implementing GPS spoofing, so it's not a quite complicated attack. So the question is, in the case of agricultural machine, how they estimate its own position. A more secure solution is to rely on data fusion. So the logic is that you mix the information from the GPS and the information from the local sensor. There are many solutions like Kalman filters and so on, so that you can well, this is a more secure solution if a GPS spoofing is not supposed to completely control the whole tractor, the whole trajectory of the tractor. And then, as I said, you can find in some cases gateways for remote control. This is not a secure solution, and in this case, you find many open source solutions to test the web, the security of web application for the gateway. For example, the one proposed by OWASP. The part on which we work more, because we thought that there is the major gap in the state of the art, was the security of the radio link. In this case, the problem is that we are facing a protocol of which we don't know nothing, but we want to assess the security of this communication. So we try to develop a procedure to do that. and of course basing on SDR car, on SDR technology. So the first step is to retrieve communication information like the frequency, the mode of the communication, and so on. Then we try to perform a set of attacks of increasing complexity. And then, as I said, connecting to the CAN bus network, we can evaluate the potential impact of the attacks on the radio link communication. And we are doing that. We did that by using some common tools and software like two common SDR car like RF1 and Blade RF, and from the software point of view, we are using mainly New Radio, but also you can find some tools in the MATLAB suite. So it's up to the engineer to choose the best solution. Starting from the most simple attack, so jamming. In this case, once you find the frequency of the communication, you just can try to send white noise over this frequency. In this case, for example, what we saw is that the transmitter and the receiver do a sort of handshake in which they choose the frequency, and they can choose a frequency within a certain range, and they use, if I remember well, 20 different channels in this range. So what's happened? It happens that if we send a simple jamming, a simple white noise over the frequency on which they are transmitted, they simply change the frequency. They do a frequency hopping. More interestingly is that the reaction of the device is different if we do the jamming with white noise or with, let's say, legitimate packets. So, for example, we discovered that trying to do a reply attack. What's happened is that if the receiver notice a jamming with white noise, it does a frequency hopping, and if it notice legitimate packet, it stops itself. So the reaction is different, and it is quite interesting. Also, you can increase the complexity of the attack, implementing, and we already didn't do that, is a responsive jamming. So the jammer just follow the frequency. It listens the energy on the channel. We know that the frequency is moving within a certain range. They listen the channel, and following the frequency the transmitter is using, it continue to jam the packet, so we can reach a complete denial of service of the communication. Second step, reply. As I said, we don't know nothing about the protocol, but we just try to capture the signal and retransmit the signal without any without having the understanding of the protocol. And what we notice in this case that this works. So we can just perform a reply attack without knowing nothing about the protocol. Also interesting is that, as I said, if and we already didn't understand well the boundary of these two cases, the tractor can stop itself if it interpret that as jamming, or use the new sources of transmission as the new controller. So what's happened in some cases, and again we are trying to understand when happens, we are able to completely exclude the legitimate joystick from the communication and substitute ourselves to the communication. This is interesting also for safety reasons, because on the joystick you have a red button that is can be used to completely stop the machine for safety reasons, of course. But in some cases we are able to exclude the joystick, and so if you press the red button, the tractor continue working on with our packets. So this is quite interesting how we can also compromise the safety of the machine. Last but not least, we didn't already perform that, but you can try to reverse engineer the protocol. There are some cases in literature actually with simple protocols, but again, it's possible. We are working on that. You can try to interpret the fields of this protocol. The steps are first to understand the modulation, and you can understand that, for example, by some data that this tool gives you. For example, the constellation. If you have a little bit experience on signal processing, you can recognize the modulation that is used. Then you have to define a start of frame and the end of frame. And once you have a series of bits, let's say, you can try to define fields of the frame. Of course, in this case, there is no strict procedures. It's a little bit more try and try, but this could be the last step of attack. So, as I said, the first step of complexity is jamming, the second is reply, and the third one is reverse engineering, and you can do that even on protocols of which you don't know nothing. So this is our work, up to us. Thank you for your attention.
Okay, thank you very much. Let me see the audience if there are any questions or any comments. Please let me invite you, because I cannot see the audience, so it is necessary to give me some feedback. Either raise your hand using the tool which can be located under the presentation screen, or simply say what you need. No, I cannot see anything, any feedback from the audience. Again, I'd like to ask you, if I can, well, this is very interesting from the viewpoint of safety, of course. And now, what the concern of the possible attackers should be? Have you identified any strategies or any intentions? I mean, if the purpose is to steal the machine or to behave in a malicious way to make it doing something which is not safe, or what the purposes and the ideas of the attackers may be in this respect?
Okay. Actually, we focus more on, this is like a vulnerability assessment, so the risk depends on the specific application. We noticed that pretty much the same architecture is used on a variety of agricultural machines. And also, for example, I remember this specific case, as I said, on tower cranes. That also use, for example, a remote control based on proprietary protocols. So the risk strongly depend on the application. For example, in the case of the tractor, you can completely control the tractor, so modifying the pathways, for example, making it cross the highway, just to do a trivial example.
Okay, and now from the viewpoint of, let's say, technical safety and security, are you self-confident enough that you are able to prevent that kind of attacks from, let's say, close distance or long distance, or what the range of the attack could be? I mean, what the attacker have to do, how much shall the attackers close to the actual device to be able to take control over it or to do any malicious activity?
Okay. It probably depends on the attack, because, for example, in the case of jamming, it depends on the power of your transmission. In the case of reply, if you have a joystick transmitting, then it depends on the power of both the instrumentation. Actually, this is a good question. The distance that we need, probably we are in the range of tens of meters or something like this.
Okay, so the perimeter can be guarded in a way, especially if the facility, I mean the agricultural location, is closed enough from the outer access. And now, how about the independent or autonomous operation of the vehicle if it does not recognize a, let's say, friendly constant control signal? I suppose this must be also handled somehow, that if the machine is left in the autonomous mode without any check activity from the center, it should stop the activity, or am I right or not?
This is a good question, because what we thought is that in some way, when we perform an attack, the machine is able to make it to goes in a safety regime. I mean, for example, if it doesn't notice a proper transmitter, probably it can stop itself, not moving, and so on. But in our preliminary test, this is not happening because, for example, we were able to exclude the transmitter and the machine is going on receiving the reply attack. So for a while, at least at the moment, we were able to control the machine even if the operator pushed the red button. So in this case, safety is not guaranteed anymore.
Okay, it's surprising to me, frankly, because any stupid drone is able to, say, land safely without the direct control from the operator. And I would suppose similar kind of safety measures to be taken also for these industrial devices. Okay, please. Is there any other feedback or question from the audience? As I can see also the hall in the conference site, no? So thank you once again, Giovanni.
Thank you.
And please stop the presentation. And now I will pass the word to the third one in a row, who is Dario Javor from Serbia. And we will talk about optimization of vehicle-to-grid service with respect to power requirements. So please, Dario, are you ready?
Okay, good morning.
Good morning. We can see your presentation. Perhaps if you can switch into the presentation window, that will be better.
Okay.
Yes, it's excellent. Please go ahead. Thank you.
Okay. Greetings to all the colleagues in Palanga, Lithuania, and to all the participants who are watching and listening to me online. My name is Dario Javor, and I employed at the Faculty of Occupational Safety from University of Niš, Serbia. The other authors are colleagues from Faculty of Electronic Engineering, Professor Nebojsa Raicevic and Professor Aleksandar Janjic, and also Professor Dardan Klimenta for Faculty of Technical Sciences, University of Pristina. I'm going to present the paper with title Multi-Criteria Optimization of Vehicle-to-Grid Service to minimize battery degradation and electricity costs. First, I will give you an introduction to the problem we have solved and give you the problem formulation. Then I will explain how we done multi-criteria optimization with constraints. Also, I will show you results of optimization and finally conclusions. Nowadays, all of us are aware of problems such as greenhouse gases emissions, global warming, air pollution, climate changes, with the consequence of environmental pollution. Development of information and communication technologies, microgrids, smart grids, and smart cities resulted in sophisticated energy management systems, shortly EMS. Renewable energy sources, electric vehicles, microgrids, and EMS are potential tools to reduce energy production from fossil fuels and to mitigate climate changes. The aim is sustainable development. Stochastic behavior of electric vehicles charging requests, as well as intermittency of renewable energy sources, cause technical and power quality problems in energy systems. New circumstances are also rising electricity prices, global strategy in the transport and energy sector to have zero net CO2 emissions by 2050, and taxes for greenhouse gas emissions and environmental pollution. Also, adoption of electric vehicles is limited by their prices, insufficient charging infrastructure, lack of confidence in driving range, etc. Increasing energy efficiency and research in the field of smart cities, smart grids and cities, IT applications, and increasing share of renewable energy sources and electric vehicles contribute to the solution of this problem. Nowadays, industrial companies, business parks, military, communities, institutions, universities, and utilities widely adopt the use of microgrid technology. A microgrid of one company having non-deferrable loads, PV panels, wind turbines, electric vehicles fleet, and its charging station with available V2G, vehicle to grid service, and it is considered in this paper. Environnomic scheduling of charging or discharging electric vehicles is obtained by solving multi-criteria optimization problem. We assumed 3 participants who would like to reduce the costs, but also to contribute to environmental protection. There are, first, microgrid owner or aggregator, the second one, electric vehicles owner, and third, distribution company. Here is a problem formulation. The company has N vehicles treated as a fleet while they are charging and discharging in non-driving hours. Vehicles are used for driving in the time interval of 6 working hours from 10 a.m. to 4 p.m. All of the considered vehicles are Nissan Leaf with a battery capacity of 30 kWh. We consider that driving range is about 167 km. Electric vehicles batteries have state of charge maximum 100% at 10 a.m. But after driving of the average distance, 55 km in 6 hours, their state of charge decreased to 67%. From 4 p.m. that day until 10 a.m. next day, electric vehicles are available for charging or discharging at the station for 18 hours. The station has 5 chargers of the power of each charger, 3.3 kilowatt. The efficiency of charging and discharging is assumed to be the same and equal to 100%. In this figure is presented the daily power demand of non-deferrable loads of industrial company per hour, and in the lower figure is presented energy production of PV panels per hour is estimated based on solar irradiation in the northern part of Serbia. PV panels have the peak power of 33 kilowatt. For wind generation is also chosen, the peak power is 33 kilowatt, and the energy production of wind generator per hour is estimated based on wind energy potential in the region of Banat in Serbia. Here are the electricity market buying prices per hour for date Tuesday, July 27th in 2021. Electricity prices have varied a lot in the last year, so it is important to reduce the electricity costs, as we we can go further. The optimization problem. Here is optimization problem. And we can see the constraints for the grid. That PG must be lower or equal to PG max, and constraints for the battery, that state of charge of I must be between state of charge minimum and state of charge maximum. Also, here is the total power demand from the main grid and power demand of electric vehicles, and the cost function is given here. In this small picture, we can see the weight coefficients. Alpha 1 for the microgrid owner. Alpha 1 is for the microgrid owner. Alpha 2 for the electric vehicles owner, and Alpha 3 for distribution company. Here is also the decision variable x of I, and x of I can be -1 for discharging, 0 for neither discharging nor discharging, and 1 for charging. Here are the results of the minimization of energy costs. In the first scenario, the microgrid has PV generator with a given electricity production curve. For the minimization of the costs function, the weight coefficients are chosen as alpha 1, 0.3, alpha 2, also 0.3, and alpha 3, 0.4. The optimized charging discharging schedule for electric vehicles fleet is obtained and at this picture. Okay, here's the total daily demand for the first scenario of the microgrid with PV generator after the optimization. And now in the second scenario, the microgrid has wind generator, no PV generator, wind generator with a given electricity production curve. And for this minimization of the cost function, the weight coefficients are chosen as alpha 1 is 0.3, alpha 2 also 0.3, and alpha 3 0.4. This means that all the three participants are treated approximately equally. Okay, in the third scenario, the microgrid has wind generator. For the minimization of the cost function and weight coefficients are chosen as alpha 1, 0.5, alpha 2, 0.5, and alpha 3, 0, 0. This means that all the three participants, that means that the costs are minimized for the microgrid owner and the electric vehicles owner. Results we can see on these two pictures. And in the last, fourth scenario, for the minimization of the cost function, the weight coefficients are chosen as alpha 1 and alpha 2, 0, and for alpha 3 is 1. This means that the costs are minimized only for the distribution company. And finally, we have a conclusion. In this paper is presented the optimization of electricity costs for one company's microgrid with PV or wind generator, the fleet of electric vehicles, and charging with available V2G service. The optimization is done based on day-ahead prices per hour from the electricity market, estimated curves of production by renewable energy sources, and daily demand of non-deferrable loads of the company. The multi-criteria cost function is a linear combination of the three functions, and it is optimized for different values of their weight coefficients. Optimization of the cost is done in program lingo. Results showed that optimal electric vehicles charging or discharging schedules can take into account benefits for all the participants. Sustainable development is not possible without efficient measures to reduce greenhouse gases emissions and decrease environmental pollution. Energy efficiency and electricity costs reduction on the global scale could be achieved only if we all give our best. Okay, thank you for your attention and for listening to my presentation.
Thank you very much, Dario.
Thank you.
Now, please, any questions from the audience or from the online participants? I can see, yes, in the auditorium, please.
So, hello, Audrius Baranauskas from Lithuania Litgrid. I represent Lithuanian TSO, and I would like to ask about the services, as was mentioned, grid, vehicle to grid. So what type of services, in addition to the cost optimization to the aggregator, could be proposed to the network operator, to the DSO in your case? Maybe you somehow evaluate additional services for power control, frequency control, or voltage control, or other flexibility services?
Okay, thank you for your question. It's a good question. For these services, other service can also can be included. And sorry, other services can also be included for frequency regulation, and it is a good addition for this work and for this optimization problem to consider other services. And flattening.
Okay, is it satisfactory as an answer for you?
Flat the curve and with some techniques such as peak clipping or valley filling or some other techniques to flat the curve.
Hello, I'm as well from the same company, Lithuanian TSO. My question is, what made you choose these initial parameters? What, for example, the times that the vehicles are being used from 10 to 4, whereas I think the typical consumer would drive to work in the morning, leave it on charge in the daytime, and then drive back for a few hours, and also leave it back on the grid for the rest of the night. Also, the efficiency that you assumed, what made you choose those parameters?
Sorry, can you repeat the last part of question? Sorry.
Oh, yeah. So what made you choose the time of day that the vehicles are being used?
Okay. These are working hours of some company. Maybe it's a taxi company or.
Okay, so it's like
industrial company.
like Bolt, for example, or City B, that you have their own fleet.
Yes.
Okay.
Yes, basically, this is what I could understand from the presentation, that this is an example of a company that owns a fleet of cars, and these are used for their business activities.
Yes.
Any other comment, please? Frankly, what I'm personally more concerned about is the sources of the energy which are used for power supplying of the chargers and of the cars. Because after all, this is, in my opinion, the main factor that influences the efficiency and in effect also the environmental impact of all these operations. But well, this would be about a different discussion, and I believe that you are doing your best to optimize the approach. So if there is not any other comment or question, I'd like to thank you once again. Please stop sharing your screen.
Okay.
And I'm going to invite the fourth presenter who is already prepared, as I can see. It is Donatas Miklušis from Lithuania, and his presentation will be basically about optimization or comparison about the estimated and real speed of a vehicle based on magnetic sensors. Am I right?
Yes. Hello, good morning. Can you confirm you can hear me?
Yes, it's okay. Also, the presentation is fine, so please go ahead.
Okay, good morning. My name is Donatas Miklušis. I'm from Kaunas University of Technology, Faculty of Electrical and Electronics Engineering, and I will be talking about identification and mitigation of incorrect vehicle velocity results based on the magnetic field sensors. So shortly, the transportation sector is an essential part of our daily life. We all spend a big part of our daily life in the congestions. And this sector requires intelligent solutions. Idea of the intelligent transportation system is to optimize vehicle traffic without major change in the infrastructure. It also includes enhancement of public safety, improve access to travel transit information, and similar goals. The essential part of intelligent transportation system is the autonomous data collecting stations. And for this purpose, a number of different sensors could be adopted for traffic flow parameterization, for the parameters, for example, the vehicle number, their speed and length estimation, and the classification by the models. Magnetic field sensors are considered to be one of the most robust to the weather conditions. They are low cost and requires relatively low installation expenses. Although during the real traffic conditions, vehicles produce very different magnetic signals, and it requires complex data processing methods. Additional sensing channels might be used to drastically increase system reliability, for example, accelerometers or piezoelectric materials. And in the end, point out that surveillance cameras, due to the privacy concern and system complexity, aren't really comparable solutions. Here in the plot below, figure 2, you can see an example of a traffic monitoring station. It has 4 AMR type magnetic field sensors. It's anisotropic magnetoresistive sensors that measures the magnetic field, and in the presence of vehicle, since vehicle has metal parts, ferromagnetic parts, it deflects the field. So in this way, we can measure magnetic field disturbance in the local area. In the upper plot, we can see an example of such an event, like the passage vehicle produce a pair of signals from 2 sensing hubs. And in this case, after applying signal alignment processing, we can estimate the delay between the signals is 23 samples. And in this case, it's about 94 kilometers per hour. So vehicle length is the main parameter for traffic classification. And in order to obtain traffic length, we first need to obtain the speed and the time value when the vehicle was above the sensor. And as we can see in this simple formula, the speed estimation error, the time error, is directly transferred to the length estimation error. So firstly, we need to estimate estimate speed with the reliable speed with a small error. And in literature, we see that other authors report the speed estimation error from 2 to 5% mean value, but it highly depends on the traffic type and layout of the sensors. In our system, we see similar result. The mean error is about 2.6%, but there are special cases when the error is above 100% and more. And to give you a better understanding, this is the example of highly distorted magnetic signatures. As you can see, there's a blue and orange charts, and they are highly distorted. So to estimate reliable speed from these signatures is the standard methods are not working usually. And what is the reason of those distortions? So the biggest contributor is the trajectory errors. Since in normal roads, vehicles are not restricted to drive only at the center part of the road. They can choose freely, more left or right. And this way, vehicles sensors reads different readings, and the signals are not identical, not symmetric. Additionally, discretization error is the big component of the error. Deceleration, acceleration while passing the detection zone, and the time delay estimation method. It was noted that when the vehicle is passing directly above the sensor hub, magnetic field sensors produce really highly faulty results. As we can see in the top plot in the figure 7, we can see the same vehicle, and it's two passage. So in the top plot, we see the distorted case, and the bottom part, we see a regular case. Therefore, we install additional accelerometer sensors to detect when the vehicle is passing directly above the sensors. And we can see in this bottom chart, the accelerometer maximum and mean value ratio, and usually it's about 1. But in the, so this is, we can see 1,000 randomly selected cases when vehicles passing. So we can see that normally vehicles are passing in the regular way. It's not driving above the sensor, but about 5% of the cases, vehicles drive directly above the sensor. And it indicates for us that is potentially the results of the speed estimation will be wrong, and we need to apply different calculation methods. Additionally, we investigate 2 more criteria to identify potentially wrong distorted signatures. So first criteria is the significance of the cross correlation results. So we compare the results of autocorrelation and cross correlation, and if signals are identical, symmetric, the peak value should be very close, and if it's not, the cross correlation will result peak value will be much lower. So in the bottom plot on the right, figure 11, we can see for high speed error values, we have only high correlation coefficient, but shows for us that our coefficient indicates that when we have high, when our coefficient is high, the speed error might be high, but it's not always the case. And the second criteria is the mismatch area. After we align the signals, we estimate the area of curvature that it doesn't mismatch, and it also means potential distorted signal. So once we know that our signal is distorted or not, we apply the speed estimation method. The most reliable method, it is cross correlation, and we can see that it's from 2.6 to 3% mean absolute error with the regular signatures, and the maximum error is about up to 16%. Point to note that in our system, we use additional piezoelectric sensors to obtain the reference speed value. If signatures are distorted, we apply different calculation algorithms. So firstly, we need to correct our signals. So we have proposed one method. It's called nonlinear rescaling. So in the left plot 14, we can see original pink signal, and then we apply nonlinear rescaling. So we see different colors, the same signal, and we suppress the peak value, and then we apply again the cross correlation method to obtain the speed, and we can see the speed values change with the rescaling factor. The next method is the signal shape correction. So initially we align signals, coarsely align the signals, and we calculate the difference, and then we subtract the difference from the higher signal, and then we apply again cross correlation to estimate the speed value. Once we obtain the reliable speed value, we can calculate the length of the vehicle. So in literature, it's well-known threshold-based method, and we propose a novel peak detection method, which idea is represented in figure 17. So firstly, we calculate the derivative of the magnetic signature, and then we have the assumption that the very first significant peak represents the front of the vehicle, and while the very last negative peak represents the back of the vehicle. So we detect those peaks, we estimate the time gap, and since we know the speed, we can calculate the length. For the practical tests, we collect a special database of the vehicles. So we collect the data of the multiple passes of the same vehicle. As is shown in the bottom chart, the same truck was recorded 16 times. So since it's the same truck, we are sure that it has the same length. And then we apply our speed estimation and length estimation methods. And as we can see in the table, our standard deviation range from 0.1 to 0.6 meters. So this is like a benchmarking that with our methods, the speed, the length, in the end, the length estimation is, the error is about 0.6 meters, absolute error. And for the last part, conclusion, I would like to repeat again that reliable traffic flow parameterization using magnetic field sensor is not a trivial task, and for practical usage, further investigation is needed. Magnetic signature of vehicle highly depends on its driving trajectory. The same vehicle might produce very different signals. Length estimation error is directly proportional to speed estimation error. Although state-of-the-art system states that the speed error, average speed error, is about 3%, but we see from the practice that it's not uncommon to have distortion, and this error can rise to much higher values. And our proposed detection criteria and estimation algorithms helps to potentially detect highly faulty cases and significantly reduce absolute error. Like it's more than 2 times. And thank you for attention, and I'm waiting for the questions.
Yes, thank you very much. Now I'd like to invite the audience from the auditorium and also from the online. If there are questions or comments, please.
Okay, my name is Vladut, and I am from Karlskrona in Sweden, from BTH. Just a small question, because you use all the time the term error, but you mean uncertainty, because accordingly to standard organization, we don't make errors. We are uncertain about the accuracy and so on. So error is like you make mistakes. So this is just small comments, but maybe in your field, you use always these errors, but I think error you make when you make mistake, but this is just uncertain, let's say accuracy. So just small comments. Could you comment it?
No, I accept, yes. Probably you're right.
Yes, thank you for this input. Any more comments, please? Perhaps we could also talk about standard deviation in terms of physical measurements or whatever is necessary to be more precise. I'm curious about the specific application, because so far we have been introduced the principles and the let's say, physical approach or the measurement approach, but how about the specific applications in real conditions where this system is expected to be deployed and what the results shall be used for in order to be as precise as possible?
Thank you. So as I point out in the very beginning that for us is the very accurate speed estimation error is not so important. It's not a speed camera because it's different purpose. Like the purpose of intelligent transportation sensing hubs, that they need to be distributed in the cities in the multiple locations, and they are like a part of the smart cities. There must be like a network of these hubs, and by input from these systems, there must be another system as a control part to control the flow. So this application will be as a sensing channel for the smart cities.
Okay, so the real problem shall be the absolute, let's say, error or deviation in how about the absolute measure in meters, which is critical for that kind of applications?
It's the most interesting application, the classification, because you want to classify passenger vehicles, trucks, and the logistic vehicles. So the length, the absolute length is important, and the range of the difference between passenger vehicles and the transportation vehicles. Usually the length is the difference is 4 meters, 5 meters, depends on the vehicles, of course, but passenger vehicles usually range up to 5 meters. And then the trucks, bus, it's usually above 10 meters.
Okay, so we need, I understand we need the preciseness to be related to the absolute size of the respective vehicle. But my concern is what absolute difference shall be a problem for the system. I mean, with respect to the application that I asked before, for example, I must not cross the sidewalk, or I must not get into the crossroad or whatever like this, right?
Mm-hmm.
Yes. So that's basically the point. Please, any other questions or comments, inputs, and so on? I cannot see any reaction. So thank you once again. Please stop your presentation. And we will go to the last one in this session, which shall be given by Ogba Buteba from Italy, from the University of, from Firenze. And this will be about DC-DC conversion using a specific approach.
Hello.
Hello, yes, we can hear you.
Hello, everybody.
Just please switch to the presentation mode.
It's clear.
Yes, that's it. Thank you. Go ahead.
Good morning, everybody. My name is Ogba Buteba. Today I'm gonna present my work, which entitled by Robust Nonlinear Controller Designed for DC-DC Back Converter via modified backstepping methodology. So my presentation outline are as the following. We start by a short introduction, then DC-DC back converter power topology, then modified backstepping controller. Then we gonna present the simulation results. After that, we gonna explain the adaptive modified backstepping controller and the simulation results, and we ending by the conclusion. So, introduction. The most important properties of DC-DC converter is its dynamic response to variation in the weight range. of operating condition. Usually the output voltage must be regulated against input voltage and load variation. For this reason, several control strategies have been developed. So the linear controllers PID represent the most used solution because of their simplicity and ease of design. Since the power converter are made up of nonlinear elements such as MOSFETs, PID controller can be a powerful solution around a fixed operating point, assuming low disturbance, but cannot be suitable for those applications where high accuracy and dynamic performance are required with the operating condition range. So to mitigate these issues, both no-adaptive modified backstepping and adaptive modified backstepping for DC-DC back converter are proposed in this work to increase the robustness, voltage control with the range of operating condition and parameter uncertainties. So first of all, we present the topology of back converter. The back converter is made up of the MOSFETs and the diodes and inductor, capacitor, and the load resistance and the input DC source. So generally, the dynamic behaviors of the back has two states. The state one, the first state is when the switch is turned on. The diode is blocked in this state. The diode it's blocked. So the input DC source act as the solid source energy into the back converter. The second state when the switch is turned off. The inductor L and the capacitor C release energy to the load via the freewheeling diode. These later resume electrical condition, ensuring the flow of current through the inductor. So in this part, the first equation and second equation represent the average state of the average state space model describing the voltage and the current dynamic, where the X1 represent the current and the X2 represent the voltage across the output capacitor. So modified backstepping control design. The modified backstepping controller generally include two steps, since the back converter is the second order system. The first concerns the design and the identification of the virtual control function, on which acts as an inductor current reference. And the low control law is designed in the second step. Identification, the first step is identification of the virtual control to obtain high performance control and to product a precise tracking and increase the robustness to load and input voltage variation and make DC-DC converter less sensitive to disturbance. The key of our work is we are adding the integral term in for the equation of the error, where the Z1 equal the output voltage minus the reference voltage. Our objective is obtain a new law control as function of the state variable, which satisfy the output voltage desired, such as output voltage equal to the reference voltage. and steer the signal of error to 0. So after some simplification, the virtual control, which acts as an index or current reference, can be expressed by the equation 8. So after that, the step to identification of the dotted circle. So firstly, we express the second error, which is the current, our current, and the reference current, which act as the virtual control. After some simplification and by the Lyapunov's function, so the final form of input based DC-DC back converter control law is determined by the equation 11. So simulation result for the modified backstepping simulation result for the first part. So to evaluate the dynamic response of the proposed modified backstepping strategy, a numerical simulation has been performed by MATLAB software. The back converter parameters and the gain of our controller is defined in this table. So for different tests have been performed to evaluate the proposed controller. We propose 4 scenarios. The first scenario, it's when our converter work in the nominal operating condition. So the figure, the second figure, present the output voltage and the current waveform under the nominal condition. So as shown in this figure, the comparison between the modified backstepping and the classical or conventional backstepping under nominal condition. Both the modified and the classical backstepping control provide the right steady state output voltage with short response time. So the second scenario, the output voltage should be regulated at its nominal value, which is 9 volts. So in the Lloyd variation, which are made in the time 20 milliseconds and increased here to 15 ohm in the 15 millisecond. So the figures show that the conventional backstepping controller, it's completely deviate when with respect to desired output voltage due to the Lloyd uncertainties, which present the major drawback of the backstepping control. So the proposed, in the other hand, the proposed control exhibit both effectiveness and robustness against the load uncertainties. The third scenario is the dynamic performance of the controller in terms of output reference, voltage reference tracking has been evaluated. The desired output voltage over time is made for 12 volts, then decreased to 9 volts. In the other hand, is decreased to 5 volts. As we can see in the figure, both conventional backstepping and modified backstepping track output voltage reference. But the modified backstepping result in fast time response. Finally, the performance of the controller under the input voltage variation are evaluated. The input voltage variation over time at 20 milliseconds from 48 to 36, then at time 15 milliseconds from 36 to 60 volts. According to the simulation results, modified backstepping control allow for fast compensation of the input voltage variation. Moreover, the output voltage steady state error are lower in the modified backstepping control. In the adaptive modified backstepping control, one of the main important features of a controller is the regulation of the output voltage at the desired value against input and load variation. In the modified backstepping design procedure, a constant load operation has been assumed in the consideration scenarios. However, in the most practical application, the load vary when the power consumption of the circuit supplied to the power converter. So to overcome the model uncertainties, an adaptive modified backstepping is proposed. This control strategy allowed an online estimation. So the equation 12 represents the estimation of the resistance load. So as the first section, the adaptive modified backstepping control has two steps. The first steps to compute the virtual control function, which represented by the equation 14, and compute the control function, which represented by the equation 17. So the same for scenario presented in the first section. On how we have been used to evaluate the dynamic response of the and make the comparison against the modified backstepping control and the classical backstepping and the conventional PI, proportional integrated controller. In the figure 1, the step response of the four controller is compared. It can be seen that the proposed adaptive modified backstepping allow for low ceiling time and low steady state error with negligible damping. The second scenario, when the back converter work in the resistance variation. So the dynamic response under load resistance variation, both classical backstepping and PE controller have the worst performance. On the other hand, the adaptive modified backstepping has a fast rejection of disturbance. The third scenario is when the back converter work with output voltage tracking. So as we shown in figure 8, the proposed adaptive modified backstepping control allowed for faster tracking for the output voltage and low steady state error if compared to modified backstepping and the classical backstepping and the PI. So the fourth scenario, when the input it's made when the back converter work in the input voltage variation. The behavior of different control strategy has been evaluated. The result of time demonstrate that the adaptive modified backstepping control is robust and efficient than the backstepping and backstepping controller, modified backstepping control, and the PA. So the fifth experience, we made the input disturbance with different mode of input, sinusoidal and ramp. So we can see, as we can see in the figure 11, that the adaptive modified backstepping is very robust. Then the modified and classical backstepping and the P. Conclusion. The main goal and impetus for this paper were to propose a robust DC-DC back converter controller based on backstepping control methodology. Starting from this later, two different control strategy has been performed. The first one, called modified backstepping, which overcome completely the major inconvenience of the conventional backstepping and perform high robust against the Lloyd variation and output disturbance, rendering the development of modified backstepping greater robustness with high efficiency. A adaptive modified backstepping has been built to achieve the control objective in the presence of non-Lloyd parameters. The comparative study demonstrated that the proposed modified and adaptive modified backstepping control strategy outperform backstepping and PE in terms of tracking performance, with now overshoot, quick dynamic response, short rising and sealing time, and minimal production tracking error. Thank you for your attention.
Thank you also. Now, I'm not sure, Darius, if we still have some time for questions.
I suppose yes, maybe
okay.
2-3 minutes.
Okay, I'm aware we are behind the schedule, but okay, please, the audience or the online spectators, are there any questions or comments? I cannot see any raised hands. No activity that would aim to speaking. Sorry for being so much practical all the time, but my question could be about the practical application of this. So I could understand that you have developed a device which is, say, a bit more robust than its predecessors. So what is your idea of its practical deployment?
The practical employment, it's so firstly we can use this controller for the maximum power point in the energy renewable. So for the practical how to say, for the practical in which part? Sorry.
Well, what specific application? Where can I find your device in the near future?
Yes. Okay. My development you can find it in the to improve the maximum power points in the renewable energy, the solar energy. So we can use it to improve and to get the maximum in renewable, the maximum points for power solar.
Mhm. Okay, I see. So I suppose that can be an example of some solar farms in Italy, perhaps, but also in other locations. Okay. Anyone else, please? Not so. I suppose someone could be interested in the technical implementation or about a theoretical background. But if not, I'd like to thank you for your presentation once again. Apologies to everyone for the slight delay, but I did not want to be so strict on the schedule because I suppose it was for the benefit of the discussion and of the relaxed atmosphere so that everyone has enough time to present his ideas. I'd like to thank you for being here this morning. I'm sending my greetings to Grand Baltic Dunes in Palanga. And the next session is about to begin in about 15 minutes. So thank you for the moment.
Thank you, Jaromir. Thank you, presenters.